WNYC Studios is supported by Odoo. When you buy business software from lots of vendors, the costs add up and it gets complicated and confusing. Odoo solves this. It's a single company that sells a suite of enterprise apps that handles everything from accounting to inventory to sales. Odoo is all connected on a single platform in a simple and affordable way. You can save money without missing out on the features you need. Check out Odoo at odoo.com. That's odoo.com. WNYC is supported by Bear. Science is about asking questions, testing, trying again. It's not easy, but it's relentless. It evolves, and that's why science delivers. Learn more at sciencedelivers.com.
Hi, I'm Ira Flato, and you're listening to Science Friday. When I think of physics, my mind goes to the basics like gravity and magnetism, or to astrophysics, black holes, exoplanets. But many of the same principles used to understand how the universe works can also be used to study Earth's climate systems, because at its core, climate change is a physics problem. But traditionally, research institutions and universities have kept these two fields, climate change and physics, separate. I want you to meet someone trying to combine them. Dr. Morgan O'Neill has spent her career with one foot in the classical physics world and the other in climate change research. And now she's on a mission to invite more traditional physicists into the field of climate research. Dr. Morgan O'Neill is an assistant professor at the University of Toronto, where she studies the physics of climate change. Welcome to Science Friday.
Thank you so much, Ira. I'm really pleased to be here.
Let's start with your story. When did the line between traditional physics and climate research start to blur for you?
Yeah, I started college in a traditional physics department, and I thought I was going to be a theoretical astrophysicist. I was certain that I would study spinning galaxies and black holes and the nature of the universe. But, when you're in college, you're just confronted with all kinds of ideas and people and fields and big societal problems. And I had kind of been casually interested, maybe a bit concerned about climate change, but I hadn't studied it much. But midway through my college career, my undergraduate studies, I realized that the physics that I was learning in class, which I thought would, naturally be applied to the spin of galaxies, could actually make a lot of progress in climate science and climate change. And I realized that those didn't have to be two separate parts of my brain. My concern for the environment and my interest in doing really hard, complex, nonlinear, beautiful physics. It turned out I could do both at the same time. And so I just had to shop, for the right classes and the right professors and research projects. And so that's what tipped me over the edge toward climate science. It is physics. All of it is physics.
So when you study hurricanes, can you use the physics to apply that to galaxies, for an example? I mean, they're spinning, they're moving.
I mean, for sure, my simple brain saw a spinning galaxy and the spin of a hurricane, and I thought, oh, it's all the same. I'll just hop over to hurricanes. And indeed, I went to grad school to study hurricanes. But no, they're very different. I would say that, fluid... So here's a challenge for the field. A traditional physics department actually rarely trains students in fluid mechanics, or some people call it fluid dynamics. And that's just how, a gas or a liquid responds to all of the different forces pushing it around and shearing little packets of fluid. That's usually left to the engineers, which I think is really a shame. I mean, the engineers for sure need to get it right. But I think that fluid dynamics should also be embraced by physics departments at the undergraduate level, not least because the interest in climate physics among physics students is exploding. Those students need access to the language that we speak in climate science, and much of that is fluid mechanics. And yet this is considered traditional physics, at least once you get to the graduate level, and many other fields. So one comparison I'd like to make is that there's, for some reason, this pedagogical division between studying Earth's climate and studying the climates of other planets. And for some reason, if it's another planet, we might call that astrophysics. People will say, oh, you're a planetary scientist, you're an astrophysicist. It is the same thing. And what's particularly exciting with Earth is that you can actually sample the wealth of climates available to a planet in our universe just by doing paleoclimate studies here on Earth. And I don't see that as a very different science than just figuring out what kind of planets there might be in, for example, exoplanet research, where we have thousands upon thousands of planets that are being discovered all the time. What do their climates look like? That's not a different problem. That's not a different kind of science than a climate scientist is asking here for what the Earth may have looked like 1 billion years ago.
Or what a geologist might look to Mars to look at the rock formations.
Absolutely, absolutely. These are very complementary fields. And the more that planetary scientists see themselves as climate scientists, and the more that climate scientists see themselves as planetary scientists, the better off we'll be. Because, ultimately it is all the same equations. And you just have to change some constants and maybe add a term here or there. It's not a big deal. And then
not a big deal for you. I think easy for you for you to say.
Yeah, everyone has access to these classes. You just have to take a few classes to do this responsibly. But yeah, I think that it would be good for the field because it would allow people with a more traditional physics training to see how natural it would be for them to step over and work on climate problems. They have the right training. They have so many tools that could be brought to bear on climate physics problems.
Well, let's talk about your quest. What physicsy kinds of questions are you trying to answer?
Yeah, honestly, I have to say I'm an aspirational climate scientist because climate usually suggests a lower bound on scale and space and time. People study the weather and then usually different people study the climate. And I'm really, really interested in the boundary between those two things. And that's because the child part of my inner brain still is really obsessed with strong winds. And the strong winds that we experience come from storms. And those are flashes in the pan with respect to climate, right? They're very small in space and time, but they're very extreme. So let's say you have a climate model and you're going to run it forward, but each little pixel in the climate model, it's a grid box, might be 100 kilometers by 100 kilometers on a side. So if that's your pixel, if you can't have any, updrafts or downdrafts or clouds or anything at all that's smaller than that very large area, you certainly can't simulate a tornado or, the peak wind speeds in a hurricane. It's not possible. But the interesting thing is we don't know the physics of the small scale storms well enough to represent the very severe events well in climate models. And so when I say I'm aspirationally a climate scientist, what I mean is I work on the physics of the very small scale because in aggregate, these small scale physics are able themselves to push the climate. And so we're working on the really small scale stuff that helps us build better models.
Yeah. Yeah, I know I said at the top that you're on a mission to get more traditional physicists into climate research. How's that going? Do you have a game plan?
I don't know how upbeat you want to be on this show, Ira.
Hey, let it all hang out.
I would say that this is a really interesting time to try to recruit physicists to come work in climate physics as a place where they can contribute. Currently, I'm the chair of the American Physical Society group on the physics of climate, and it's our mission within the APS to grow the climate physics community and to serve as sort of a home for physicists coming from traditional backgrounds to come and see all of the ways in which they can contribute, whether they're condensed matter theorists or fluid mechanics experts or radiation or quantum materials experts. But it's a challenging time because of the current very strong ideological filter of the federal government on whose research is valid and worth funding and acceptable in the public discourse. And now we see that there is a very strong attempt to end federal funding of most or all climate research. So now we're asking climate scientists to, hey, maybe add a conference. Why don't you come to the Global Physics Summit of the APS? When they themselves don't know if they'll ever hire a postdoc again. They don't know if they'll ever get a grant funded, if they talk.
It's that bad.
It's really bad. It's really bad. Some of my colleagues in the States are paralyzed and just can't sit down and write an NSF proposal because they don't know how they can propose their work in a way that won't get keyword gutted,
No kidding.
If you study climate change and then you say in a proposal, this is my idea for studying climate change, and you know that the term climate change is going to prevent you from getting funded, how do you proceed? How do you ensure that your first year PhD student will have funding in 4 or 5 years? How do you ever post an ad for a postdoc again? It's very grim. It's horrible. And I'm really grateful to be in Toronto, where our federal government, at least for now, continues to see enormous value and urgency in climate science research. So it's really challenging. It's challenging for us to grow the group on the physics of climate. But I have to say, in spite of these challenges, they're totally worth it. It's really exciting. And the research is just so important and so cool right now. And so the door's wide open to physicists. But there are these structural challenges. And for sure, one of them is asking climate scientists to stretch themselves even thinner when they're not even sure they can go to conferences anymore, period, because the money's running out. So yeah, it's pretty serious.
Are you inviting all other American physicists to come join you in Toronto there?
Oh, I would love to. I mean, I have to be, I'll tell you, honestly, my colleagues and I have received a number of confidential queries about whether, new positions will be opening up or if certain institutes or departments will be growing. There's a lot of interest, and I understand it because that's why I'm abroad now too. I used to be in the States.
Right.
But of course we can't take everyone, and nor would I want to. I mean, the U.S. needs really great scientists, and the U.S. needs really excellent universities to train all of its phenomenal students. And so it's really tragic that so many people feel the need to leave just to be able to do their own research. I mean, it's a tragedy. It's a gutting of this world historic triumph of publicly funded scientific research and higher education. And it's nothing to celebrate. I am so sad about it.
Well, I don't want to end on a down note, but this interview started out in one spot and it landed in a very worthwhile other spot, getting out your views about what's going on in American science. And I thank you for your work and for your opinions.
Thanks very much, Ira. I've appreciated this opportunity. What a pleasure to speak with you.
You too, Dr. Morgan O'Neill, Assistant Professor and Atmospheric Scientist at the University of Toronto and Chair of the American Physical Society's Group on the Physics of Climate. This episode was produced by Rasha Aridi. We'll catch you next time. I'm Ira Flato.